So that's quiz number 4. So we really just have one more quiz, and then after that you can stop taking quizzes if you like. Though I recommend that you do keep taking them. Because remember, I'm only counting the top 5 quizzes. I'm hoping, I'll guarantee you, what did I guarantee you, 6 or 7? Yeah, I'll guarantee you 7, but I'm hoping to get 8. And that, like, if we're really pushing hard, we'll try to get 9. So keep that in mind. I know regarding the midterm assessment deal, the midterm evaluations, that some of you said you didn't like all the quizzes, but the quizzes, I'm going to keep pushing the quizzes. Like, I would love for you to get as many quizzes as we possibly can. Because, one, it just helps the numbers work out better, because I take those top 5 quizzes. And then, 2, it really does help you do better on the exam. A couple other things that came up on those midterm assessments, one of which I can't really do anything about, but I just want to encourage you in it, that people said that the exam seemed tricky. And I understand that the exam was different from previous exams, but they're just different, right? But they're over the same content. And so as you're going through the old exams, think about, well, what is the principle behind this question? And then ask yourself not just what is the answer to that question, but what's behind it. That you want to understand the content behind the question. Reading the book will be a good way to prepare for the next exam. And reading through the notes is a good way to prepare for the next exam. You can do very, very well on the exam. It takes some preparation, that you have to know the material pretty well. All right? The other thing that people commented about, and we can certainly change this, several of you, 5 to 8 of you or so, you look like you have a question. We'll answer it in a second. Okay, 5 to 8 of you said that you want review sessions for the exams. And we can do that. We can set aside some time, 20 minutes or so in the class, but then we can also have an out-of-class review session that would be longer, an hour. So I'm certainly willing to do that. We'll just do it the day before the exam or the class period before the exam, and we'll review. That'll be time for your questions, and then I'll also just sort of give you a summary of all the material that's on the exam. In short, of course, not all the details, but I'll give you a summary of all the material that's on the exam. I haven't done that before in this class. I don't know why. I do it in my other classes. But there's a lot more math in the other classes, and students often struggle with math. It's not just you guys. So that's why I'm doing it. And we'll do this one too. That'll be good, right? Yeah? All right. I appreciate your feedback. If you ever have any questions or thoughts, just let me know. I'm open to it. All righty. Any concerns, questions? I did super on that quiz, 100%? No.
How about we redo this quiz when we come back?
Huh?
Let's redo this quiz when we come back.
Redo it? It's the same quiz?
I mean, why you already give us a big hand up?
Really, you're so thoughtful. Really
know, right?
appreciate that. No, she's like the nicest person ever. Dave, you could think. Okay. Yeah, so you get your grade, you divide by 10 and multiply by 2. Hold on, give me just a second. I'll carry on about yourself. All right, folks, so up till now, we've been looking at work and energy. We saw work and how you can have positive and negative work. Positive work means that you're giving energy to a system. Negative work means that you're taking energy away from the system. We talk about how friction does negative work. We saw the work energy theorem, and that is that when I do work on a system, I give it energy. And we usually think of that in terms of doing work on a system. Remember, work is force times distance when they're in the same direction or parallel to one another. And when I do work on an object, I give it kinetic energy. And we find that that's that 1/2 mv squared. We had a bunch of different kinds of energy. Kinetic energy, potential energy, that's the energy of position. When an object has the potential for motion, then it has potential energy. This has potential energy. When I let it go, it moves. We saw also lots of other kinds, nuclear, electrical, chemical, elastic potential energy. And we'll see those again as we move through the semester. We saw the conservation of energy. That was where we move up and down. And you'll certainly see a question like that on the test where I ask you, where does this object have the most kinetic energy? Where does it have the most potential energy? And you'll need to pick out the point on that roller coaster or something similar and tell me, where is the kinetic energy the most? That's where it's going the fastest. And where is the potential energy the most? That's where it's at the highest point, because that's where it has the most potential for motion. We talked about this whole closed versus open system. Closed systems, no energy goes into that box. If I have an open system, energy can come in and energy can go out. And we can make a system closed just by thinking about bigger and bigger areas. Because if we make it as big as the universe is a closed system, no energy coming in or out of the universe. So at some point, you expand your view of the system until it becomes closed. And usually you don't have to expand it as big as the universe, but just, you know, the human body we generally think of as a closed system, although it's not exactly, we'll see. We talked about power. Power is energy over time, or work over time, and our energy over time, we measure it in watts. And then we talked about efficiency. You'll have an efficiency problem, so make sure you look at some of those where I give you the efficiency and the amount of work put in, and then you have to tell me how much comes out or how much is lost. They'll be simple numbers, but I want you to know how to calculate that. We've done temperature scales. You need to know Fahrenheit, Celsius, Kelvin, how they're defined. And then calorimetry, where we talked about phase changes and changing of temperature. No calculations on that, but you'll need to know how Q, for example, is proportional to M, C, and delta T for calorimetry, and then know how we require all this extra energy to do phase changes. And that's, for example, why steam at 100 degrees Celsius is so much more damaging than a water burn, because there's so much more energy in steam. That's that whole latent heat of vaporization. And then our 3 methods of heat flow, conduction, convection, and what's the other one? Radiation. We'll see all those ideas come up again in this section in some form or another. Energy and temperature and these forms of heat transfer. Okie dokie? Yeah? Yeah. When is our next step?
March 25th.
I'm guessing, but let's look at the calendar. I don't know exactly. I just sort of wait till I get about a week out. And it doesn't even have to be on a whole chapter, like we can do a half. I know, I still have to look at the calendar. Let's see, so what is today? 28th? Yeah, so we have 1, 2, 3, 4, 5, 6 class days. What are we in right now? Chapter 3? We had all of chapter 2 on the last test, right? No, we'll probably get a little bit into chapter 5 as well. I'm not sure. Oh, electric potential. Yeah, we'll probably get a little bit into chapter 5. Drop day, by the way. When is drop day? 3/29. Okay, good. So we'll have an exam just before the drop day. So you'll have a good, firm feeling on what your grade is in the class before the drop day. Okay? What? I don't want any drops in this class. Like, if you're thinking about dropping at this point, don't. You really need to come talk to me. I'll talk to you about it. Okay? All right, energy in the body. So the governing principle for this, when we're talking about energy in the body, is the conservation of energy. And we've already seen the conservation of energy. That just means that the total amount of energy that you have in that system remains the same. That it's always the same. That's like the roller coaster. It always had the same amount of energy. It just sort of transferred between two different parts. And remember, conservation of energy assumes that you have a closed system. And so this must account for energy that leaves and enters the system. But we just said that we think of it as a closed system. But there is, in fact, some energy that comes in and goes out of our body. Right? How does energy go into our body? Food. And that's really the only way that energy goes into our body. But we put off energy in our body in a couple of different ways. And we'll see that expressed in terms of the metabolic rates, the basal metabolic rate and then also the total metabolic rate. And that will include not just sort of how our body functions, that's most of the energy that we consume running our heart, our brain, and our other organs, but then also additional activity and the amount of energy that our body uses. But most of the energy that our body uses is just to live. Also, when you do work, you consume energy. When you move around, when you exercise, or when you're just active, that you do consume and burn energy in your body. And so this is that when I do work, I cause a change in energy. Work is equal to a change in energy. That's the work energy theorem. Right, we saw that before, that if I do work on an object, then I change its energy. And that happens in our body, that when we do work, when we apply a force times a distance, we actually do work, then that causes a consumption of energy within our body. Our body can use energy for macro and micro purposes. Macro would be like exercise, or not just exercise, but just sort of moving around, being active in the way that we are. And then also micro purposes. We'll talk about this in terms of our BMR, our basal metabolic rate. I'll define that a little bit more later. But as I said, that's the processes that are going on in your body, the processes that must occur in order for you to live. Food is the primary source of energy. It can be stored for short term, which is glycogen, and long-term storage, which of course is fat storage, and both of those are important. Glycogen and long-term in the form of fat storage. But food is our primary source of energy, and our bodies can store that. When we're talking about food, the unit of energy, I think this was on your quiz, the unit of energy is the calorie. Notice that I used a capital C. 1 calorie is actually equal to 1 kilocalorie. So it's actually 1,000 calories. We use the capital C for calorie. So a calorie, a little c calorie, little c, is the amount of energy required to raise the temperature of 1 milliliter of H2O and a milliliter of H2O is equivalent to 1 gram of H2O of water. Used to be that we defined, remember mass standards? Well, we said that the standard for mass now is based on the Planck's constant. Used to be based on that cylinder in France. Got a question on the last test about that. It used to be, before it was the cylinder, the mass constant was based on a liter of water. And they said if you have a liter of water, that is a kilogram. And it turned out that wasn't a real great mass standard. It just wasn't very accurate. It didn't allow us to make very accurate measures of mass, when you're trying to measure the masses of subatomic particles. And so, but that's why you have this correlation between a milliliter of H2O is a gram of H2O, because that was our original standard for the kilogram. Did y'all know that? Did you ever wonder why a milliliter is a gram? You've heard that before, right? No, maybe not. That the density of water is 1 gram per cubic centimeter, or 1 gram per milliliter. Yeah, just a little tidbit for you. So to raise the temperature of 1 gram of H2O by 1 degree Celsius. And just to remind you, this is a throwback to our calorimetry. Q is equal to MC delta T, that I require 1 calorie to raise 1 gram of water. Water has a certain specific heat, pretty high, by 1 degree Celsius. Oh, I guess the specific heat of water is 1, actually. Okay? 1 calorie per gram degree Celsius. Food calorie, as I said, is equivalent to 1 kilocalorie. And we write that as 1 capital C calorie. Now you have 3 sources of energy in foods. Do you know what they are? Right, carbohydrates, lipids, and proteins. Carbs. These all have a certain energy density. Carbs are not the most energy dense. They are about 4 kilocalories per gram. Lipids, which is really just a fancy name for what? Fats, right? So lipids are fats. These are the most energy dense. That means that per unit mass, they provide the most density. And y'all know that, right? Like, your grandmother has a big bucket of lard on her countertop, does she? No, my grandmother did. But big bucket of lard, that's a very energy dense substance. Like, if you pick it up and you eat it, it's a lot of calories just in a little bit amount. I mean, I never ate it. She would make biscuits and stuff, and they were delicious. But anyway, so with the fats, they have a energy density of about 9 kilocalories on average per gram. And then finally, proteins, you know, lean meats, eggs, nuts, stuff like that, 4 kilocalories per gram. Now, you don't have to memorize these numbers, of course, but I do want you to know that lipids have more than twice the energy density of the other two. And you need to know that lipids are fats. So that's just a fancy name for fats. These are called nutrients, these food sources of energy. We have other nutrients. Other nutrients include, yes, vitamins and minerals. And the most important nutrient of all is water. Vitamins, minerals, and water. So those are also nutrients too, but not sources of energy for your body. Energy from carbs is delivered most quickly to the body. Which one's the most slowly? Right. The fats, the lipids. Nutritionists, and I think this changes, and you guys might know more about this than me, but this was the last that I saw, is that nutritionists recommend a diet that's about 50 to 60% carbs, 20 to 30% fats, and 15 to 20% protein. I know there are probably some of you that don't follow that diet, that you have something much different for health reasons that you think that's better, but this is usually what nutritionists recommend. Some people eat a very high protein diet, for example. What are some sources for each of these? We have carbs. What are some sources of carbs? Bread, rice, pasta, sugar. Right, sugar is a big source of carbs. So bread, grain, rice, pasta, Coca-Cola, which is mostly sugar. It's like one of the worst foods that you consume, like one of the worst soft drinks, one of the worst things that you can consume. Because there's so much sugar. It's like, what? She made a joke. All right, carbs, lipids, oils, fats, and then proteins. What are some sources of proteins? Eggs, yeah. Meat, fish. There are some vegetable sources of protein. What are they? Beans, right? Tofu, which is made from soybeans. All right. No, tofu's not disgusting. It takes whatever flavor you put with it. Oh, you should get it over at Roots. You should have it over at Roots. They do pretty well, I think. Y'all eat at Roots?
Where's that?
There's a whole line.
There's a long line.
I know. There's a long line. It's in the cafeteria.
Oh, I don't know. It costs like $8.
No, it's like $5 if you're on the plan.
I'm not.
What's it for?
I live in Tiffany.
Oh, well, all right. More for me.
I don't have a good point.
All right. I have a video I want to show you. All right. There's a lot of thought that goes into, especially for these professional and college athletes, and to what they eat and how they just take care of their bodies in these times of practice, but then throughout the year as well. Let's see here. So let's take a couple questions. 3 sources of energy from food. What are they? Carbohydrates, what, and what? All right, let's do about 5 or 10 more seconds. I'll stop at 25. 25. Oh, good job. Awesome. B is right. Did you hear about the Italian chef who died? Did you? Yeah, he passed away. All right, and let's try this one. So the answer here is carbohydrates, proteins, and lipids. Let's try this one. It's sort of going back to what we did before, but if you double the thickness of the material, what's the new rate of thermal conduction? Which of these is the thickness? That's really the question when I ask. A, delta T, B, or K? Which one is the thickness, and what happens when you double it to Q over T? That's my rate of thermal conduction. Okay, which of these, A, delta T, K, or G, is the thickness of the material? It's not A. A is the area. A is the cross-sectional area. So we talked about how I have these 2 materials that are in thermal contact with one another by some material that connects them, and this distance is D, and A is the cross-sectional area. So if it's a bigger material, like if it's a wider across, then I have a bigger cross-sectional area. So really asking about what happens when you double D. Except nobody's changing their answer. What happens to this quantity over here if I double this quantity? Oh, come on, you don't need to be good at math. If I doubled this quantity, what happens to this quantity? It was 2 kilocalories per second. What is it going to be now? That's a little bit better. I'm going to stop at 210. 210. All right. Okay, A is right. Because if I have a 2 in the denominator over here, this is in the denominator, and in order to have the same thing happen over here, I have to have a 1/2. Listen, folks, I would expect a question like that on the test, that looking at that equation, and we had some others, right, where if I change one variable, what happens to the others? And there are 2 questions that you have to ask yourself when you have a question like this. One is it in the numerator and denominator? If I doubled this, I would have a factor of 1 over 2, because this is 1 over 2 over here. And then the other question you have to ask is it linear or is it quadratic? That means, is this number squared or not squared? Because if b was squared, what would this be over here? It would be a 1 over 4, right? Okay? Yeah. Go ahead.
We don't know. Why would it be 1 instead of 1/2?
Oh, because it's asking the rate of conduction is 2 kilocalories per second initially, and then you double the thickness of the material. What's the new rate of thermal conduction? It was 2, now it's going to be 1/2 of 2.
Okay.
All right?
1/2 of 2.
Yeah, 1/2 of 2. It's reduced by a factor of a half. It was 2 before, but now it's going to be 1. Is that what was tripping y'all up?
Yes.
Okay. You're going to see a question similar to that on the test, okay? Okay? This exact question? It'll be similar.
They're all similar.
They're all similar, right. Okay. Work done by the body. So, as you know, macroscopic work, that's sort of the work that you do with your muscles, it's not really a big part of our energy consumption. They said those guys, they were consuming what, 2,500 or so calories? Or no, a normal person is 2,500 calories that you burn, but most of your energy actually goes into running your body. So that's about 1,500 calories. One of your questions was, what is the basal metabolic rate? That was about 1,500 calories. Now you can change your basal metabolic rate. We'll get to that in a minute. But the macroscopic work, nonetheless, that's work done by the body. For example, if I want to climb 1 flight of stairs, so say I have a flight of stairs, and I'm going to climb it. I'm, say, moving up a height equal to 3 meters, and let's say that I have a mass equal to 70 kilograms, then I can figure out the amount of work that's required to move up those stairs. I would say that U is equal to mgh. That's the amount of gravitational potential energy that I'll have when I'm at the top of the stairs. And that's going to be 70 kilograms times 10 meters per second squared. That's just G times H, which is 3 meters. So it's at 700. 2,000, about 2,100 joules. And that's about approximately a 0.5 food calories, a 0.5 kilocalorie. So if you climb a flight of stairs, the energy is required about a 0.5 calorie, not that much, right? Then if you climbed 200 flights of stairs, how much energy would be required? Well, it takes a 0.5 calorie to climb 1 flight. Only 100 calories. Let's put an exclamation point, because that don't seem right. Right? Have you ever done like the stair climber, and they tell you how many calories? 200 flights. That's a lot of flights of stairs, right? And does it tell you you've only burned 100 calories? That's like one of those little packs of cookies, the 100-calorie pack. You know what I'm talking about, with like 3 cookies in it? Yeah. That's not very much. So you say, that just don't seem to be right. And it's not right, because it turns out that your body is not 100% efficient, right? That it takes more energy to put in than you get out. Tabulated charts show that calorie burning for 1 hour of stair climbing is about 400 to 600 calories. I think you could probably do 200 flights in 1 hour, right? On the Stairmaster, on the stair climber deal. What's that? I don't know. Is an hour about 200 flights? Do they tell you that? I don't do it. My knees are shot. But anyway, yeah. So why the discrepancy? Muscles are very inefficient. They typically have about a 20% efficiency. So if you want to get out 100 calories, you would have to put in like 2,000 calories. No, is that right? You'd have to put in a lot more. You'd have to put in 500 calories. Like if I wanted to get out 100 calories, I'd have to put in 500 calories. So you climb the stairs for an hour, and you burn, 500 calories. By what amount have you increased your potential energy? So this is an efficiency problem, right? I have put in 500 calories. I know that I'm 20% efficient. And I want to know then, how much energy do I get out? Let's try this as a clicker question. 400, 200, or 400, 300, 200, 100. All right, let's try this. Now, I know the answer has to be less than 500, so I didn't give you any options, because I can only get out as much or less than I put in. If I'm 20% efficient, 20% is a fifth, right? 20 over 100. How much energy do I get out? All right, only about 15 of you have the right answer. Feel free to ask your neighbor what they put. You're only 20% efficient. That means that you only get out 20% of what you put in. Now remember, 20%, that's 20 over 100. That's the same as 1/5. Megan?
You're not the same, okay?
You can do that.
I thought that was easy though. Like, one of these things is not like the other. Yeah.
All right, let's stop at 140. Oh, y'all did well. That's good.
Can you show us something?
All right, very good. D is right. Yeah, this is your input energy. This is your efficiency. And it helps to think of these efficiencies. I'll give you easy numbers like 20%, 25%. It's helpful to think of those in terms of fractions. So 20% is equivalent to 1/5. 25%, for example, is equivalent to 1 over 4. So I'll give you some nice easy numbers like that. But so I know that my output energy is going to be 1/5 of my input energy. That is to say 500 calories times 20%, or I can write it as 500 times 1/5. And 1/5 of 500, you break 500 into 5 parts. Each of those parts is 100 units, so 100 calories. You don't need a calculator to do that. I assure you. Just do a little practice. And all right. I know this. I mean, you don't really use a whole lot of math, but you will use math.
Don't ever do math.
In your careers, you will use math in your careers. If you go on to your graduate program.
I'll have a calculator.
Okay. Be prepared to do a question like this on the test. Yes, test question. Big star. All right, let's look at metabolism. Metabolism, it describes the biochemical actions, chemical, in the body that use energy to build up and tear down substances. The metabolic rate is the rate of energy usage in the body. And to measure the metabolic rate, it's kind of interesting. You can measure the metabolic rate in different ways, and there are various instruments that can sort of measure your pulse and then estimate what your metabolic rate is. But the best way to measure the metabolic rate is to submerge a person in a tub of water. And then measure the rise in the temperature of the water. It's kind of like a bomb calorimeter, right? That's what they did, except they're not exploding you. That you put in this little container of water, and then after a certain amount of time, they measure the change in temperature of the water, and they see how much energy your body is putting out. Like, not just the temperature of the body, but sort of how quickly it's putting out energy into the water. And our metabolic rate can change with age, with activity. We'll talk about it in a bit. The basal metabolic rate is the rate at which body converts energy into thermal energy. While resting. This basically is just the energy required to live. So the BMR includes, things like your major organ systems, your brain, your heart, your lungs, your skin. Just keeping those things going is your basal metabolic rate. Your basal metabolic rate is usually about, well, let's do this. We'll try this. Let's try this question. You can do the math, but you probably know the basal metabolic rate. Which of these is close to our basal metabolic rate? The way that you would do this, by the way, I wouldn't ask you to do this math on the test, but I know that my BMR is about 65 calories per hour. And I know that in one day there are 24 hours. Notice how the hours cancel out there and there. And it leaves me with my total basal metabolic rate, my BMR, for a day. All right, good. Stop at 47.
Yeah, that's easy. That's analysis. But like,
All right.
I just know it.
Okay, good. B is right. My basal metabolic rate is about 1,600 calories, based on this rate of 65 calories per hour. You can change your basal metabolic rate through changes in just sort of how you live, the diet that you eat, the amount of activity that you do. I found that my BMR went up a lot. About 5 or 6 years ago, I started lifting weights, and that changed. Yeah. Mm-hmm. Yeah. And so I know my wife sort of thought this was strange or funny, or I don't think funny is the right word, because it used to be that I was kind of cold natured. Like at night, I'd have a couple blankets on me. But now, after I started lifting weights, it's like every night, no matter if it's 65, 60 degrees in my house, like I just have to throw off everything. And my wife, in the meantime, is over there with like 4 blankets on top of her. It's like, why is it so hot in the house? Y'all going through menopause or something, crying out loud. But you can change your basal metabolic rate, and then that will change the amount of calories that you consume. But then you typically have to consume more calories too. All right? Or you just lose weight, yeah. But you have to eat. All right? Ironically, young people and tall, thin people have higher BMRs because they're growing, like young people are just growing, so a lot of energy goes into just making them bigger. Or for tall, thin people, which doesn't really seem fair, right? The tall, thin people that they have high BMRs because they don't really need high BMRs, right? Because they're tall and thin. But the reason they have high BMRs is just because it requires more energy to heat their bodies. They have a very large surface area, and so they just lose a lot of heat to the surroundings. So it requires more energy to heat their bodies, which has a large surface area. That's why you'll see these tall, thin people out at, the restaurant eating huge hamburgers and French fries, and they're still tall and thin because their BMR is just so high. Not so much that they exercise a lot, but just their BMR is high. All right, the total metabolic rate is the total energy to run your body. And this includes any activities that you engage in. So there was a question on the test. Our TMR is more than our BMR. Right? Actually, TMR is equal to our BMR plus the energy from our activities. BMR may require about 1,600 calories a day, which is most of the calories you consume. But the TMR can be a bit higher, depending on the amount of activity, up to maybe 2,500 calories per day. But those football players, quite a bit more than that. So they might be eating, I think they said up to 10,000 calories in a day. 5, 6, 7, 8, 9,000 calories. I want you to notice, however, that the BMR is the bulk of your calories. Burned every day. And so while exercise is great for your body, to really manage weight in a normal person, there are other issues that can cause you to have weight gain. But to really manage weight, you have to cut consumption of calories. All right? Exercise is an important part of that because, like I said, as you exercise, as you're more active, it can actually affect your BMR. And if you're able to raise your BMR, then that will cause your body to the overall calories it consumes every day will be higher. There's this guy on the radio, the Get Fit guy. Have you ever heard of him? He has a podcast. You heard of the Get Fit guy? Oh, well, he has a thing. It's a podcast. It's kind of interesting. Like, if you're in human performance stuff, you should look it up. If you look on Stitcher or whatever, Apple, podcast or whatever. But every day he has like a 5-10 minute podcast about the body. And one of the podcasts he talked about, he's kind of crazy. Like, he's a little bit crazy. Like, he says, for example, that one thing that you should do every single day is lift something heavy. And so he keeps a barbell in his kitchen that with a lot of weight on it that's heavier than he would normally lift. And he lifts that every single day, just once. Like, he works out and stuff and does stuff like that, but he just lifts this barbell every day. But another thing that he does to raise his BMR, you're going to love this. I bet everybody's going to start doing this. To raise his BMR in the morning, he takes as cold a shower as he can stand. Yeah. Because, the BMR is related to how much energy you give off. Right, yeah. And sort of set, he says, I'm not sure if this is true, but he's, you know, he's a trainer and all that. But that it actually resets your body and thinking, oh, I have to put out this extra energy to heat up every day. As cold as you can stand. And around here, cold water, we don't really get cold water, but where he lives up north, like the water is cold, cold. I know, I mean, in the summertime you take a cold shower anyway just because it's like lukewarm. All right, let's try these questions. The one on the left, what is BMR an abbreviation for? Oh, sorry, it's spelling error. It's not an abbreviation, it's an abbreviation. What does BMR mean? Oh, that up here. Y'all click in? Yeah. Huh? Oh, I don't know. It won't be Thursday. No, it'll be the week after.
Okay.
All right? Yeah, don't worry about a quiz right now. I mean, you can be reading ahead. It'll be the next chapter, but it won't be the Thursday after we get back. No. Alrighty? Y'all are amazing. BMR, basal metabolic rate. Let's do this other one, then I'll give you a joke. The food unit of energy is what? Which of these is the unit we use for food energy? All right, stop at 25. 25. Looks like, oh, good, you changed your answer. Good. Good, B is right. The food calorie is the big C calorie, and that's equivalent to 1,000 calories. Or we could also write it as 1 kilocalorie. That's what kilo means, 1,000. All right? Why can your nose not be 12 inches long? Because then it'd be a foot. Yes. All right, let's look at body temperature. Homeostasis. I think we had a question on the quiz about this, did we? Homeostasis? And y'all got it right, of course? Yeah. Homeostasis. The body's temperature is very regular. The core temperature only changes slightly with exercise, like those football players, although that's kind of extreme to change that much, or with illness. So when when you're sick, you can have a fever as your body fights away that sickness. The outer portions of the body can vary a lot based on the environment. Remember, like when I had the infrared thermometer and I measured the temperature of my hand, it was only like 80 degrees Fahrenheit. So the outer portions in the skin, they can vary, but the body's core temperature is very, very regular, and we call that homeostasis. There is a homeostasis, I understand. I don't understand it exactly, but I think there's a homeostasis that's on a cellular level too, right? Like cells experience this too, where they have a controlled environment, or is it related to the temperature? What is it? What does that mean on a cellular level?
It has to do with enthalpy and entropy.
Which is just energy, right?
Yeah.
Enthalpy is just energy.
There's a formula for it.
A formula. Oh.
It's like
These people, man.
G, a change in G is the discrete energy equals H minus G S times T.
It's like there's a formula for everything. Isn't that right? What's up with these people? They ain't got nothing to do. That's right. So the outer portions can change a lot. Sources of heat include the metabolic processes in the major organs. And that includes, you know, liver, heart, brain, skeletal muscles. And then heat is lost through the skin by our three: conduction, convection, and radiation. We can lose heat through all of these: conduction, convection, and radiation. And then I'm also going to include here evaporation. But evaporation is really a form of conduction. That I have water on my skin, and then if it's not too humid, which is often very humid, and that's why around here that when you sweat, you just sort of get really wet. But if it's not too humid, that water will evaporate, and it will take away an immense amount of energy from your body. And remember that latent heat of vaporization, it takes so much energy in order to change the water to a vapor. Well, that latent heat of vaporization is drawn away from your body, causing you to cool off. So evaporation, by conduction, because it's touching your skin and pulls that energy away from your skin, is a big, big way that we lose energy. Although it's not the most significant way. The most significant way that we lose energy is, do y'all know? Radiation. Right, so we're like big light bulbs. Like y'all are all sitting out there and you're light bulbs that are emitting about 40 watts of power in an infrared light. So you have all this infrared radiation coming off of you. Just like there's light, visible light coming off the light bulbs in this room, that you're giving off infrared radiation. So you can have heat loss of the body through conduction, organs that are a higher temperature than the skin, so if I think about my body, no arms, I have my heart, I have my lungs, I have my liver down here, I think. These are really high temperature, huh?
Black liver.
These are a high temperature, so I have high temperature here, and that means that heat is going to move in that direction. Right, like moving from the fire up to your hand. The heat will move from a high temperature to a lower temperature. And so I get conduction of heat from the high temperature organs out to the surface of the skin, which is a lower temperature. Also, as we said, evaporation is a form of conduction. Convection, cool air, comes into contact with the skin. You stand in front of a fan when it's hot, and that's very effective at cooling you. Partly it's effective because it allows that sweat to evaporate off of you. But also it's effective just because the convection of air around you. And then radiation, warm objects emit infrared radiation. We'll have a whole chapter on this, so we'll talk about it more. But this is the big one, right? That they actually emit infrared radiation. And then, as I said, evaporation through sweating. I've already answered this question, so we're not going to do it. But evaporation is what form of heat transfer? Conduction, right. Alrighty. Yeah.
Okay. They don't have to, but they want
Yeah, y'all can have a great break. Right.
Yeah.
Hold on just a second.